Welcome to our podcast, and we're going to be talking to you about working with different length operands. So in the DLX machine, we have 32-bit registers, 32-bit addresses, and 32 bits of data in each memory location. So when we're working with numbers smaller than that, we need to increase them to fit. Now this happens in the case of instructions such as add immediate or the immediate comparisons, and several other instructions like that, which are the immediate instructions. And then also things such as jump, which is a long immediate instruction. Now, the immediate instructions, you put in a 16-bit constant, and the long immediate instructions, you put in a 26-bit constant. So we need some way to get these 26-bit and 16-bit numbers up to a 32-bit number to properly fit in the address space.
So to overcome differences in operand length within the context of unsigned values, we can simply extend the length of the value by adding zeros to all preceding positions, and as we're about to show, this will not change the value of the operand. Now, within the context of DLX, this extension will always be applied in order to reach a length of 32 bits, but we can demonstrate the utility of zero extension by only converting a 4-bit number to an 8-bit number. This number is equal to 11 in base 10. Now if we want to add zeros to the front of this, we can see that as long as this is specified to be unsigned, we still have our desired value. We can also do the opposite of zero extend, thereby removing the preceding zeros. And again, with this reverse process, we do not change the value. Now, supposing we are working with signed numbers as well, as we inevitably will be in any complex program. This value is -5 in 2's complement, a notation. But if we want to extend this with zeros to reach a full byte, then we end up with 11 again. This is clearly no good.
To solve this problem, we use a process called sign extension. This involves copying the most significant bit to all the places to its left until we reach a desired length. As you can see here, we have a 4-bit number that we want to increase to 8 bits. To do this, we copy the most significant bit, which happens to be the 1, across into all other positions. As you can see, this still results in -7. When we use +7, we also grab the most significant bit and copy it across, and this also results in +7. We can also do the reverse of sign extension by trimming any copies of the most significant bit to get the desired length, as long as there is 1 left behind to keep the sign of the 4-bit number the same. So we can trim here, and we're still left with a 4-bit number that remains the same. These two 8-bit numbers, however, will not work, as when you trim to 4 bits, the most significant bit on the 4-bit number changes, leaving a completely different value than what you started with. This can, however, be trimmed to 5, 6, and 7-bit numbers.
These algorithms are also used in other instructions, such as in the conversion between bytes, half words, and words, as well as right shifts, where the arithmetic right shift uses a sign extend and the logical right shift uses a zero extend. Thank you for watching our podcast.